Hello everyone. So this video is part 6 of elimination reactions. So in this video we will compare E1 and E2, and after that we will also compare elimination versus substitution. So for the videos of substitution you can also go through all the 6 videos that are under substitution reaction category. Okay, the link of the playlist of substitution reaction that will be given in the description box. So let's see E1 versus E2, which mechanism will take place. So first we will quickly brush up the E1 elimination and E2 elimination. So E2 is concerted. So here we have taken a general structure of a molecule which is R2CX and then CHR2. So here CX bond, that is the leaving group carbon bond, and CH bond, both the bonds will be broken simultaneously. Fine. The base is attacking the base. The base is attacking the proton. Then there is a formation of CC bond and the CX bond is cleaved. So we are getting this alkene. But when it is E1 elimination, there are two steps. First, there will be formation of carbocation over this carbon, because in the first step the CX bond will be cleaved. In the second step, that is after the formation of carbocation, this CH bond will be removed by the base, and again we are getting the same molecule. So there are some factors that affects the E1 elimination or E2, that is which will be predominating. The first point that we will discuss is base that we are using for elimination reaction. So if your base is stronger and more concentrated, then E2 will be favored over E1. Just remember the rate expression of E2 and E1. In E1, it is rate constant into the concentration of your substrate only. But in E2, there is also the concentration of the base. So that is why if your base is very concentrated, that is the number of base molecules in a particular volume in the reaction medium, if it is very high, then E2 elimination will be favored, and also by strong base. So if your base is very weak, probably it will go to through E1, because it doesn't matter whether your base is strong or weak in case of E1. But again I am saying, if it is stronger, obviously if you are taking the same reaction condition, same substrate combination, then obviously E2 will be favored over E1. So that is all about base. The second point is the nature of the substrate. Nature of the substrate means you can say the alkyl halide. So here this is our substrate. So presence of electron releasing groups, it favors E1. Now electron releasing groups, they are mostly present in case of tertiary alkyl halide, and as you are moving towards primary, this electron releasing group that is decreasing. It is not just always alkyl group, maybe some other electron releasing groups are also present. That depends on your substrate. So electron groups, why it is favoring E1? Because in E1 there is a formation of carbocation intermediate which requires electron releasing group. Then only the positive charge that will be stabilized. But in case of E2, there is no such formation of positive charge. Actually there is no intermediate formation in case of E2. So presence of electron releasing groups, it is not making any change in case of E2. So if your alkyl halide is primary, then it will be mostly E2. Okay, because in primary there is no stabilizing factor of carbocation. So that is why it is E2 only. Now when it is secondary, then both may take place, but E1 will be favored. Though again I am saying there are some other factors. Here we are focusing only on the nature of the substrate, but some other factors are also there. Suppose base, leaving group, etc., temperature. So all those things also we have to consider. But if you are focusing only on the nature of the substrate, this particular factor, then obviously E1 will be favored. Now in case of tertiary alkyl halide, E1 is favored, but E2 can also occur. Now you can think that why E2 is occurring here from a point of view that tertiary alkyl halide, it is very hindered substrate, right? And when elimination is taking place, obviously some portion from this tertiary alkyl halide it is removed. So your bulkiness of the starting material, that is decreasing. So obviously it is favoring the product formation. And in tertiary alkyl halide, the double bond that is formed, that is also highly substituted. So that is why elimination will be favored. So these points are common for both E1 and E2. So that is why some E2 can also take place. Okay. So for E1, basically there is some preference, tertiary greater than secondary, greater than primary. But for E2, there is no such preference, though in some cases, in some books, you will see that it is again the same preference order, that is 3 degree, greater than 2 degree, greater than 1 degree. But mostly this order is applicable for E1, not for E2. Fine. So this is the second point, that is the nature of substrate. Now the third point is solvent that we are using. E1 requires an ionizing solvent. We know in E1 there is carbocation intermediate formation. Now ionizing solvent means that can promote ionization of the substrate. So suppose our substrate is Rx, and if Rx bond is broken, we are getting the carbocation R plus. So this type of ionization, faster the ionization, better will be it is for E1. So ionizing solvent, it can help to ionize the substrate Rx to form R plus and X minus. So that is why ionizing solvent, it favors E1. So E1 requires ionizing solvent. So obviously polar protic solvent, that will favor E1. Okay. So polar protic solvent, what is polar aprotic solvent? All those things are already discussed in the videos of substitution. Fine. Now if your solvent is less polar, just forget about protic aprotic for some time. Just focus on the polarity of the solvent. Suppose it is less polar, then E2 can also occur in less polar solvent. Why? Because if you compare E1 with E2, in case of E2 in the transition state and in case of E1, there is a particular full positive charge formation in the intermediate. So obviously it is more polar. So though polar solvent is required in case of E2, but if it is less polar, then also there is no such problem. It can occur, that is E2 can occur, because just compare the transition state of E1 and E2. E2, the transition state, it is not so polar compared to the E1. Okay, that is why it can also occur in less polar solvent, but obviously polar aprotic solvent. Now we are highlighting on the term aprotic, because aprotic solvent, it will increase the rate in E2, because in E2, in the rate expression, there is mention of the base also. So if our solvent is if our solvent is protic, so it the attacking base, it will be in less free condition. Okay, there will be hydrogen bond formation, it will be in the cage of the solvent, but that problem will not arise if our solvent is aprotic. So polar aprotic solvent, it increases the rate in E2 elimination. The fourth point is leaving group. Both E1 and E2 are possible in substrate that possesses a good leaving group. Obviously, because the concentration of Rx, that is mentioned in the rate expression of E1 as well as in the rate expression of E2. So obviously the leaving group, that is X, that matters, if it is good or bad. If it is good, it is good. It is preferred for both E1 and E2. But again, we have to remember one factor, that other factors can have control. So we will see one example where the leaving groups are same, but the substrate, if you look at the design of the substrate, that is different. So here we have two different types of substrate, and the first substrate E2 is taking place, in the second substrate E1 is taking place. So in the first substrate, see, this is our leaving group N plus Me3. Here also the same leaving group, but in the first case E2 is occurring, because see, if you remove the leaving group first, the positive charge will be here, okay, which is primary. But in the second case, if you are removing this, the newly formed positive charge, that is 3 degree. So obviously here E1 will be favored. Okay. This is 3 degree. 3 alkyl groups are there. So that is why we are saying, though leaving group here are same, but as other factors have control on the mechanism, so in the first case, E2 is taking place, but not in the second case. Now, we will summarize all the points that we have discussed. So we will compare all the factors here. So let's quickly brush up. E1 elimination, this is the rate expression, only the substrate Rx. So that is why it is unimolecular. But here the base term is also present, so it is bimolecular. Leaving group first departs and carbocation is formed as intermediate, and in the second step, which is first step, in that step removal of hydrogen is taking place. But E2 elimination is concerted process, it is a single step process. Both the groups, that is proton and the leaving group, they are eliminated simultaneously. So this I have already said that preferred is 3 degree greater than 2 degree and 1 degree because of the carbocation stabilization. It is maximum in case of 3 degree, but in case of E2 there is no such preference. But in some books you may find that the same preference is written, but mostly it is applicable for E1. Now what about base? Here no strong base required. Just look at the rate expression. It will be clear why strong base is not so important here. But here stronger and bulky base in high concentration is required. So strong and high concentration, that is okay. But why we are also talking about bulky base? Because if suppose your base is not bulky, then there is a chance that the base that you are using, then it will be more nucleophilic. That is static hindrance now it is low. Suppose your base is not bulky, so static hindrance low, then there is a chance that it can lead to some substitution also, substitution reaction. So that is one reason. Another reason is if the base is not bulky, then E1Cb may also take place, because in E1Cb the first step is the removal of the hydrogen. So it can easily, as it is less bulky, it can easily approach the hydrogen. So that is why if the base is bulky, E2 will be major mechanism that will take place. Now what about leaving group? Strongly dependent on the leaving group. Now here in case of E2 also leaving group is important. But one very important difference is, suppose in your starting material there it is alcohol, so there is OH group present. Now you can change the OH group to a better leaving group OH2 plus if you are using some concentrated acid. So it will be protonated. But hydroxyl can never be a leaving group in case of E2 elimination, because in the first case when OH2 plus is removed there is a carbocation formation, but in case of E2 there is no such thing. So that is why when we are talking about this type of reaction, that is mainly dehydration, removal of H2 minus H2. So that mainly goes through E1 elimination. And the last point is no stereochemical requirement, but in case of E2, the leaving group, that is H and X, they must be trans to each other. That is the anti-periplanar arrangement that we have discussed in detail in the video of E2 mechanism. So that is up to this point, that is all about E1 versus E2. Our next topic will be elimination versus substitution. What are the factors that lead to elimination or substitution? So here we have the first point is basicity of the nucleophile. The more basic the nucleophile, the more likely that elimination will be taking place and substitution will be less. So obviously it is true, because what is the main difference between base and nucleophile? Base is some species that is always searching for some proton, but nucleophile is such species that is always searching for some atom other than hydrogen. Now as in organic chemistry we always talk about carbon, so that is the basic difference between base and nucleophile. Okay, so in case of elimination, you know, it is mostly the hydrogen, sorry, not just mostly, it is always hydrogen that we have to remove. So obviously we will talk about basicity. So if you have some species that can act as base as well as nucleophilic, but if its basicity is more compared to nucleophilicity, then elimination will take place. That is, elimination will be favored over substitution. So here we have example. In the both examples, you can see our starting the substrate is common. That is 2-chloropropane we are using in both cases, but our base is different. Here it is ETO minus ethoxide ion, but here it is CH3CO2 minus, that is acetate ion. Now ethoxide ion, if you compare with acetate ion, it is strong base and it is weak base. Now how you will understand it easily? Ethoxide ion, if you just think about the corresponding acid, if ethoxide ion is conjugate base, the corresponding acid is ETOH, and in case of acetate ion, the corresponding acid is HOAC, that is acetic acid. Now if you compare ethanol with acetic acid is more acidic, so its ionization is faster compared to the ionization of ethanol. So that means that acetate ion, it will be stable compared to the ETO minus ion. That is why the ionization of acetic acid is faster. Okay, so more stable means it is weak base. It is weaker compared to ethoxide ion. So our substrate is same, but our base is different. So that is the reason. See, in the first case, as our base is strong, we are getting elimination product 75%, but substitution product 25%. But when your base is weak, now you can say that it is switching towards more nucleophilic. Then our substitution product is 100%. Okay, so this is the difference. That is, by changing the basicity, whether weak or strong, we can change the type of the reaction mechanism, that is whether elimination or substitution. Move to the second point, that is the bulkiness of the nucleophile. Bulkier bases or nucleophile, here we are using both the terms together because we are comparing elimination and substitution. Base, this term we mostly use for elimination, and nucleophile we mostly use for substitution. So if it is bulkier, then it can induce elimination on a substrate. So sterically hindered bases and nucleophile, they will be good proton abstractor compared to its nucleophilicity. So why it is better proton acceptor when it is bulkier? Because if you compare hydrogen and any approach towards the carbon where there is some substituents already present, and hydrogen it is attached to only carbon only. So obviously the approach of the nucleophile or base, whatever you want to use, that is the term, whatever you want to use, the approach towards this hydrogen, obviously it will be easier if this nucleophile is very bulky compared to the approach towards this carbon. So this is the reason. So here we have example, same substrate we are using, but in the first case this is HO minus our base. In the second case it is tertiary butoxide ion, that is the base. Just I am writing the charge over oxygen. So obviously it is more bulky. So approach towards the hydrogen, that is, this is alpha, this is beta. So approach towards this hydrogen for this bulky base, it will be easier compared to HO. So that is why in the first case we are getting substitution product, but in the second case we are getting elimination product. Another example, our starting material is 1-bromo-pentane. Here our base is very bulky. Again we are using tertiary butoxide ion. So 15% substitution product, but 85% elimination product. So again elimination is winning over substitution because the base is bulky. The third point is nature of the substrate. So elimination is favored with an increase in branching of the carbon chain, because when there is increase in the branching of carbon chain, the alkene that will be formed as product, it will be very stable because of hyperconjugation, and it will be highly substituted also. So this is the first reason. Another reason is presence of stabilizing groups. If it is already present in our starting material, for example phenyl, vinyl, etc., so that will also favor elimination reaction, because the newly generated double bond, suppose it is just beside the vinyl group or pH group, then there is a chance of resonance, okay, conjugation. So that is the driving force that elimination it will win over substitution. So here the driving force is conjugation. So here we are using 1-bromo-2-methyl-propane and our base is methoxy. So this is a substitution product and this is a elimination product. Okay, so see here branching is very high, isn't it? This isopropyl group is present here. So that is the reason here elimination is more than substitution. So this is the nature of substrate. Another example that is also, you can see our starting material, there is some branching. So as branching is present, we are getting elimination product 80% but substitution product only 20%. The fourth point is nature of solvent. Now nature of solvent, first talk about polarity of the solvent. A less polar solvent favors elimination over substitution. Now this term, fact that is mainly useful for E2 and SN2. Because in E1 and SN1 in both cases there is some carbocation generation which is common for E1 and SN1. So obviously polar solvent is required. So less polar solvent favors elimination over substitution. This is mostly applicable for E2 versus SN2. Why? Because if you compare E2 with SN2, in case of E2 it is 4 center mechanism. That is, the charge is dispersed in the transition state over 4 atoms. But in case of SN2, your nucleophile is approaching the carbon which is containing the leaving group. This is actually 3 center. Okay, actually I should also write the base here, that is approaching. So if you compare the transition state of E2 and the transition state of SN2, obviously the charge is more dispersed in case of E2 compared to SN2. So that is why if your polarity of the solvent is less, that will favor E2 mechanism over SN2. And now if you come to protic or aprotic solvent, then aprotic solvent allows increase in the base strength. Now it is very clear, because if it is aprotic, the base molecule, it will be in more free state. It will not be in solvent cage by formation of hydrogen bond. So if it is in more free state, the attacking tendency will be high. Okay, so that is from the point of view of whether the solvent is protic or aprotic. The fifth point is very interesting. Just see, in physical chemistry we know that del G equal to del H minus T del S. This is the free energy, this is the enthalpy, and this is the entropy. Now with the entropy term, T is multiplied, that is temperature. Now for a favorable reaction, we know that del G must be negative. Now when to del G, if you want this value as negative, one thing that enthalpy should be very negative or del S should be positive, and T value it should be high. Fine. Now we know that in case of elimination, entropy change is high compared to substitution. Why? Because in elimination, starting from 2 species, you are getting 3 species. But for substitution, starting from 2 species, after the reaction also you are getting 2 species. So entropy change is more in case of elimination. Now as del S is already high in case of elimination, and now if you are increasing the temperature, so after this multiplication, this value will be very high. That means there is already a negative sign, and if the value is very high, even if suppose del H is not very favorable, suppose it is positive, but if this value is so negative that it will overcome the less favorable del H, suppose if del H is less favorable, so ultimately del G will be negative. So high temperature, it will definitely favor elimination reaction over substitution. So look at this example. Here again we have taken same substrate combination, but only the difference is in the temperature. In the first case it is 45 degrees centigrade, in the second case it is 100 degrees centigrade. So in the first case we are getting elimination product 53% and substitution 40%. So it is almost same. And in the second case we are getting elimination 71% but substitution 29%. So now elimination is higher than substitution because we have increased the temperature. Okay, so that are all the factors that may have some role whether substitution will be predominating or elimination. Now just one table which is regarding the alkyl halide nature. Based on alkyl halide, if we compare SN1, SN2, E1, E2, then which mechanism will be operating. So this is based on only on the alkyl halides. So first focus on primary alkyl halide. Primary alkyl halide, it is good for SN2, that we already know. So primarily it will be substitution, because in case of E2 we have seen it not so important whether it is 1 degree, 2 degree or 3 degree, unless there is steric hindrance in the alkyl halide. So suppose sometime it may happen, for example neopentyl group, though your carbon is that is primary, but still as there is a large group present, so that is why, because of the presence of steric hindrance in the alkyl halide, in that case elimination may take place. Okay, so that is a special case. And what about SN1 versus E1? They cannot undergo both of these, because the carbocation which is common for SN1 E1, in both cases it is generated, but if it is primary it will be very unstable. Now secondary, both substitution and elimination are possible. Now stronger or bulkier the base and higher the temperature, the greater is the percentage of E2. Now increasing temperature, why it is so, we have just discussed in the previous slide. And if the basicity is high, obviously basicity term that is related to elimination, so elimination will be favorable. Here also in case of SN1 E1, both may take place. And the last one, that is a 3 degree alkyl halide, on the elimination, because SN2 it is not possible in case of tertiary. This very bulky alkyl halide, so approach of the nucleophile in the transition state, it will be very problematic. And SN1 versus E1, both are possible in case of tertiary alkyl halide. So that's all about this video, that is E1 versus E2 and then elimination versus substitution. Fine. In the next video we will also see some more examples, some different types of examples of elimination reactions, and also after that we will discuss some problems. Until then, goodbye, and if you find the video helpful, please like, share and subscribe, and thank you for your time.